We type a prompt, and a hyper-realistic image materializes in seconds. The process feels immediate and purely digital. Every calculation takes place inside a network of warehouse-scale data centers, where rows of servers run around the clock to sustain the AI ecosystem. This chart shows the projected electricity demand for the 6 leading AI firms. By 2030, these companies are expected to consume up to 295 terawatt-hours of power, roughly 1% of total global electricity demand. Artificial intelligence functions as a heavy industrial process, requiring a vast physical foundation of hardware and energy to generate code. These facilities are concentrated in a few specific global hubs, with extreme density in regions like Northern Virginia and Ireland. This clustering creates intense grid pressure. In these hubs, data center demand could absorb nearly half of the local electricity generation. Training models requires 99.995% uptime. Because intermittent renewables like wind and solar cannot yet guarantee that constant reliability, many operators rely on natural gas plants to ensure the servers never stop. The rapid expansion of this digital infrastructure is actively reshaping regional grids and creating new challenges for global decarbonization goals. Running these high-density server clusters generates intense heat. Cooling them consumes millions of liters of fresh water, often placing data centers in direct competition with local communities for water security. Beyond these daily operational costs, the physical construction of the facility carries its own environmental debt. This is known as embodied carbon, the emissions generated before the building is even finished. Embodied emissions can account for over 40% of a data center's total greenhouse gas footprint over its entire life cycle. The core and shell of a single 200-megawatt facility require large quantities of structural steel and concrete to support the internal systems. The concrete poured annually for global data centers generates roughly the same emissions as running up to 3 natural gas power plants for a year. Net zero targets remain difficult to achieve, as long as the building infrastructure itself carries a permanent multi-ton carbon debt. Inside these buildings, hardware is governed by a rapid upgrade cycle. Companies discard servers every few years to maintain computational speeds necessary for competitive AI training. This visualization shows the projected impact of those upgrades. By 2030, the AI industry is expected to generate 16 million tons of cumulative electronic waste. These discarded servers contain a mix of valuable metals like gold and palladium, alongside hazardous materials including lead and chromium that require specialized, difficult recycling processes. The industry is generating a hardware graveyard and is expanding faster than our current global capacity to recycle or repurpose it. While the demand for AI computation continues to grow, the physical systems supporting it can be redesigned to reduce their footprint. One approach is agri-voltaics. Co-locating data centers with solar panels on active farmland allows for clean energy production while maintaining the land for agricultural use. Extending the lifespan of servers also reduces the waste stream. Running hardware for an extra 1 to 6 years in less intensive secondary computing roles allows for maximum use before disposal. Solutions also require policy changes, specifically mandatory reporting that forces companies to accurately measure their full embodied and supply chain emissions. If AI is to help solve global challenges, the physical infrastructure housing it must not contribute to the problems it is intended to address.